Namaste everyone. Yeah, we have studied radioactivity. We have seen how radioactive nucleus emits alpha particle, beta particle and gamma rays. What happens to the nucleus and how it undergoes disintegration. And after a certain time, what is the number of atoms remaining in the sample? That's what we were discussing about. There is a number of atoms remaining in the sample after a certain time. We got an exponential function there. Mathematical function. So it is like this: when the time is 0 seconds, the number of atoms in the sample were n naught, correct? N naught were the original number of atoms in the sample when the radioactivity just started, and after t seconds the number of atoms in the sample were n, and lambda is a constant called decay constant, and if decay constant is very large for a material sample, then it decays very fast, and if decay constant is very small, it decays very slowly. That's the meaning. And you know that it starts from radioactive decay law, which states that the activity of a sample. What do you mean by activity? The rate of disintegration. Rate of disintegration, that means activity of a sample dN by dt is directly proportional to the number of atoms in the sample at that instant. If you have more number of atoms in the sample at that instant, you will have more activity. That means more number of atoms will be disintegrating per second. So dN by dt is directly proportional to n, or dN by n must be equal to, we have to write what is dN by dt equal to first. dN by dt is equal to, the rate of disintegration is equal to minus lambda n. Negative sign indicates that the number of atoms are decreasing with time, and lambda is a constant called decay constant, and rearrange this, dN by n is equal to, what you will get, minus lambda dt. Now integrate this from n naught to n, and it is decreasing, remember, when the time is increasing, right? Time increases from 0 seconds to t seconds. So when this is n naught to n and this is 0 to t. So when you integrate this, 1 by n, differentiation of log x is 1 by x, integration of 1 by x is log x. So and now it is to the base e, and I write ln n, and the limits are from n naught to n is equal to this integration. Here everything is constant, minus lambda into dt, and you can retain 1 here. When you have 1, integration of 1 dt is t, integration of 1 dx is x, and differentiation of x is with respect to dx is 1, and so what you have now here, minus lambda is a constant, and integration of 1 with dt is t, 0 to t. So put the limits and write the value. What you will get, hope you can see it here, right? Yeah. Now the answer is ln n, upper limit minus lower limit is equal to minus lambda t minus 0. So ln n minus ln n naught, log a minus log b, log a by b, and log is usually based to the base 10. Log to the base e is called ln, right? 2.303 to the into log of base 10 is ln. Okay, ln n by n naught is equal to minus lambda t, and n by n naught is equal to e to the power minus lambda t. So e to the power is a mathematical function. That is the way in which you write it. For example, we will complete this first. N is equal to n naught e to the power minus lambda t. So this equation shows that the number of atoms in the sample decreases exponentially with time. What do you mean by exponential decay? What do you mean by linear decay? So we will see that. Now this is the way of expressing the lane and bringing the lane here. It is very similar to explaining something in the 10 to the power. For example, 100 is equal to 10 to the power 2, correct? And if you take log to the base 10, under the base 10, if you take log of 100 is equal to 2. That's how we write it. This is the method of writing. So if log of 100 is 2, the meaning is 100 is 10 to the power 2. This is to the base 10. Similarly, we have ln, which is log to the base e. E is an exponential function. It is a mathematical function. As if we have y equal to mx plus c. It's a mathematical function. It's a mathematical equation which represents a straight line. Similarly, e to the power x represents exponential function. How is e to the power x representing a mathematical function, and how is it vary? How does it vary with the variables? For example, here time is the variable. Lambda is not a variable. Lambda is a decay constant. Suppose you take some amount of radioactive material, and it will have some decay constant. As the number of atoms in the main parent element, as they go on decreasing in the main source that you have taken, lambda doesn't change, because the original atoms will be as thorium only. Some thorium atoms will get converted into some other radioactive material, but original thorium will be as it is. So that sample will have the same lambda. Now log to the base 10, this is how we represent. So if 100 is equal to 10 square, then log to 100 to the base 10 is 2. So this base is usually not written. If ln is written, then log to the base e. So if ln n by n naught is minus lambda t, then n by n naught is e to the power minus lambda t. And okay, suppose you want to take ln x, for example, ln x, then it is 2.303 log x, log to the base 10x. So if you want to take it from the base 10, multiplied by 2.303. I think you might have used this in chemistry. Whatever it is, you will come to know about this later in mathematics also. So this is how the equation says. This equation shows that the number of atoms in the sample decreases exponentially with time. What do you mean by decreasing exponentially with time? Suppose if I have given an example how the number of how do I donate every morning, right? As I wake up in the morning and as I start outside, whatever I have in my pocket, 50% of the money I donate. But that's what my principle is. If it is so, this is only an example. Don't come to me and don't wait for me to come out of my house tomorrow and wait for me so that you will get 50% of the money. This is only an example. You can't get it. So now how does it go now then? So if I have some 4,000 rupees in my pocket, so today I will donate 2,000, and tomorrow I have 2,000 in my pocket, I will donate only 1,000, 50% of what I have. So the amount of money I have donated has become 1,000 only. Previous day I donated 2,000, 1,000 now. Now tomorrow I have only 1,000 rupees, I will donate only 500 rupees now. This is somewhat like exponential decay, and that is explained by another term called, we will come to this again, half-life. We define a term called half-life for any radioactive material. What do you mean by half-life? Half-life of a radioactive material is the time. This represents time. It is not half of full life, right? Don't take it as half of full life. What do you mean by half-life of any radioactive material? So uranium has a half-life, thorium has a half-life, radium has a half-life. Every material is characterized by half-life. Its half-life is a constant, right? Half-life is always a constant. Decay constant is always a constant. However it undergoes decay, its decay constant remains the same, half-life remains the same. What do you mean by half-life? Half-life is the time in which time taken by the sample to reduce to half of the maximum value. If you have some n naught, it should become n naught by 2. How much time does it take? Then it is called half-life. For example, in the example I have given, 1 day is my half-life of money. The half-life of my money is 1 day, because every day I lose by 50%, correct? If I have 4,000 rupees, by the end of this day, that means by evening, I have only 2,000. Next day evening, I have only 1,000, 500, 250, like this. So half-life is the time duration in which the total number of atoms in the sample reduces to half of the previous value. Original value, not previous value, the maximum value. Not original also, maximum value. Out of the maximum value, to become 50%, how much time does it take? That is called half-life. So time in which number of atoms in the sample reduced to half of the maximum value, that time is called half-life. Please try to remember all these things, whether they are in the syllabus or not, don't worry, because this idea is very useful in capacitors. When you go to charging and discharging of capacitors, in that chapter, again this is needed, entirely different chapter, but idea is same. Okay. Now, if half-life is represented by a letter T, I want an equation for half-life. Now, how do you write the equation for half-life? You can write it like this. Now, what is half-life? Half-life is the time in which this number should be n naught by 2, correct? N naught is the original number of atoms we have started. N is the number of atoms after any time t. It need not be only half-life, any time. If half-life is 1 day, after 1/4 of the day, what is the atom? How many atoms will be remaining after 1/4 of the day? How many atoms will remain after 1 hour? How many atoms will remain after 6 hours? So you can use this formula for any time, finding the number of atoms in the sample after any time. But exactly for half-life, when time t is t, that is exactly half-life, the number of atoms remaining in the sample should be half of the maximum value, correct? If you take this time t as capital T, which is termed as half-life, the number of atoms in the sample remaining at that time after one half-life should be half of the maximum number, that is n naught by 2. So if you use that formula here, then n is equal to n naught e to the power minus lambda t is the general formula. Then this n should be n naught by 2, because you know that exactly after half-life the number of atoms in the sample will become half of the original number. This is original number. Here the number of atoms should be half of the original number. So n naught gets cancelled, and half is equal to 1 by e to the power plus lambda t. You know this, 1 e to the power minus x is 1 by e to the power plus x. That implies 2 is equal to e to the power lambda t. Remember this one? How did we get this actually? Lane, here it is, right? We have that. Lane n by n naught is equal to minus lambda t. What is n by n naught is equal to? E to the power minus lambda t. Again, then what is meant by minus lambda t? That is lane n by n naught. So if you want to bring this down, minus lambda t, you bring this e to the power here, that becomes lane n by n naught. So how can you write this? 2 is equal to e to the power lambda t. So bring this like this. Lane 2 is equal to, how much you get? Lane 2 is equal to e to the power, not e to the power, lambda t, just lambda t, isn't it? Right? So if you bring lane here, 2 is equal to e to the power lambda t. That's what we did here. Lane n by n naught is equal to n minus lambda t. So what is n by n naught? E to the power minus lambda t. So lane 2 is equal to lambda t. But value of lane 2, if you look into the Clark's table, you have lane values also, logarithmic values, lane values. So you can do that also. And statistics students may be knowing how to get e to the power and all. Okay. Now what is lane 2? The value of lane 2 is 0.693. You can take it from the logarithmic book also. So take the log of 2 and multiply it by 2.303. You will get the answer, because I have written somewhere that the log of any number multiplied by 2.303 gives the lane. Okay, 0.693 is equal to lambda t. Then what is half-life? Half-life is equal to 0.693 by lambda. Half-life is equal to 0.693 by lambda. Right. This is the relation between half-life and decay constant. So 0.693 divided by the decay constant gives the half-life. Very important relation. Suppose you are asked to obtain the relation between half-life and decay constant. Then you can do it like this. So half-life and decay constant. Half-life, define half-life first of all. It is the time in which number of atoms reduced to half of the starting value, initial value, or maximum value. So it's the time in which number of atoms become half. So n should become n naught by 2. Then you have to replace this t as capital T. So 1 by 2 is e to the power minus, but 1 by 2 is, you bring this downwards in the denominator, e to the power plus. That implies 2 is equal to e to the power lambda t. Lane 2 is equal to lambda t. Then 0.693 is lambda t. T is equal to 0.693 by lambda. Very important equation. So half-life is 0.693 by decay constant. Okay. Now you have to define decay constant also. What is actually decay constant? I said decay constant is a value which says whether that sample decays very fast or very slowly. See, we need samples which decay very fast as well as very slowly. For example, if you want to find out the age of a fossil, or suppose you get a very old bone or very old wooden piece. While digging somewhere, you got a very old skull, you got a very old wooden piece. You want to know how many years old it is. That is very, very interesting way in which it is found out. we know the half-life of carbon 14 usually. It is I think it is something like 1600 years. So half-life of, if you know the half-life of carbon 14 and compare it with the activity of the carbon 14 now in that sample. So study how much of carbon 14 shows activity, or how much activity is shown by the carbon 14 in that bone which was alive long back, right? So take the sample which you have got now, calculate the activity. There are methods of calculating the activity of the sample. Number of atoms disintegrating per second, you can calculate it by some methods. So you calculate the activity of the sample carbon 14 in that bone. Now that bone or that wooden piece was alive some years earlier, long back it was alive. When it was alive, there was a activity of carbon, right? The activity of carbon or the number of atoms disintegrating per second in the carbon might be very large or long back. It is as if you look into the student, he is reading like anything, or he or she is reading like anything. 3 chapters per day, 4 chapters per day. That means I think the examination may be tomorrow or day after tomorrow. A student who is preparing for the examination is wandering in the room and is not, he or she is not preparing at all. Most probably the time length is more. Now you have more time for the reading. Similar, but it is a reverse way, right? As we have more holidays, we read less. But here it is not so. When the bone is alive, when the wooden piece is alive, the activity of the sample will be highest. The number of carbon atoms in the sample will be highest. But as the time passes, the number of carbon atoms will go on decreasing. And more interesting is, sir, we take carbon in many forms, right? Now when we take carbon, when we are alive, in our bone, or when a tree is alive, in the tree, whatever the carbon content, won't it be undergoing decay? Won't it be exhibiting radioactivity? Yes, but as the amount of carbon goes on decreasing in a live tree or a living person, that living person or living tree will inhale carbon continuously. As the amount of carbon content goes on decreasing in a living bone or living tree, the inhaling of carbon goes on continuously, and the amount of carbon in our body or a living tree is a constant. Now the wooden piece that you have got, or a bone piece that you have got, when it was alive, it was having the activity of carbon or the number of carbon atoms same as the bone which is alive now. Am I right? The bone which is alive now, or the tree which is alive now, should have had which is alive now is having the same amount of carbon atoms as this wooden piece when that was alive, isn't it? You can compare it. A live tree now, a live tree which was thousands of years back, both were having the same amount of carbon atoms when they were alive. Don't you agree this argument, right? A living tree now, a living tree 20,000 years back, now it is just a piece of wood. That tree which was living thousands of years back, 10,000 years back, whatever it is. That tree when it was alive, it was having the same number of carbon atoms as a living tree now. So what you have to do is, you have to take that wooden piece or the bone, compare the number of atoms in this bone or wooden piece with the live tree now, or a live live bone, a live person's bone. Now the activity or the number of atoms in the carbon atoms in this sample has been reduced. So compare it with this one. Compare it with the living tree or living bone now. Now what is N and what is N naught? N naught is the number of carbon atoms in the living tree now. This was also a living tree once upon a time. Compare it with N naught. Now N is the number of carbon atoms in this wooden piece now. Because this wooden piece was alive long back, and N naught is the original number of atoms, carbon atoms in that. Now the number of atoms in this sample is N, because it has been dead and the inhaling of carbon has been stopped. As soon as the inhaling of carbon has stopped, number of carbon atoms have gone decreasing. And once you know the decay constant of our half-life, even if you know half-life, you can calculate what is decay constant, correct? You bring this lambda here, you put T half here, you can calculate decay constant. You know number of atoms in the sample now. You know number of atoms in the carbon atoms in the sample when it was alive, which is same as the number of carbon atoms in the live tree now. You can put it here. Lambda you know. Why can't you find out T? You can find out how much time has gone. To find out the age of fossils, we find the carbon percentage in the sample. Why? Because carbon has a long half-life, large half-life. It takes years together to get reduced to half. But imagine a person who is just dead. Suppose a person has committed suicide. We come to know that he has committed suicide later. Okay? It may be after a few hours. It may be after a few days. We will come to know it. And we want to know exactly at what time. Exactly means I am not talking about exact at what second, what minute. Not like that. But maybe 2 hours earlier, or just half an hour earlier, or yesterday, at what time he has committed suicide. Then the doctors and persons who will interrogate this one, and they will test that sample in his body, which will deteriorate, which will decay very fast. That means its decay constant is very small, because that will be easier to accurately find out accurately the time in which that person has committed suicide. That gives an accurate answer. Now you can't test the carbon atom present in the sample, because carbon atom takes to reduce to half, it takes long years, many years together. So that is not the best chosen sample. Our body contains different samples of radioactive material, but they are not harmful. They are not as strong as some uranium or so. But that contains some samples which will deteriorate. So when the person is alive, he will be inhaling carbon, and the carbon atoms will be deteriorating. But as he inhales carbon, again the number of carbon atoms will be uniform, and that will be same in all the live materials, almost uniform. So once the person dies, the inhaling of carbon stops and the carbon atoms start deteriorating. And of course, in a very short time period, if you want to know what is the decay period and what is the time, if you want to know, you have to choose the elements in the sample which have very less decay constant. So samples having less decay constant are chosen there, which decay very fast. And samples which have long decay time, which decay very slowly, are taken for materials to find out their age, and when it is in the terms of many years. So we have samples, that's where we have started this explanation. We have samples which can decay very fast, and samples which will decay very slow. Both and all type of materials are available in this nature. So that's how it is used. So this is how much useful formula this is now. Biologists use this very much to find out the age of fossils. And even in medical field, it has a very good application. Okay, now, right. So this is half-life. Now, I want to know exactly what is decay constant. What do you mean by decay constant of a material? Which material has got more decay constant? That means what? Now, that decay constant, if you want to define, what I will conclude is, I'll take this equation, n is equal to n naught e to the power minus lambda t. Now, simply, without any reason, I'll take lambda is equal to 1 over t. Simply, I will take it 1 by t. You will understand why did I take it as 1 by t. Let decay constant be reciprocal of time, because I have told, if decay constant is very large for a material, if it is a large number, big number for a material, the meaning is it decays very fast, means it takes less time. If the decay constant is very small for a material, it decays very slowly. What do you mean by that? It takes a larger time. Slowly means larger time. Faster means shorter time. So it is the reciprocal of the time. Now put lambda is equal to 1 by t. What you will get? N is equal to n naught e to the power minus 1. Am I right? Because, or I will substitute this 1 by t into t, because lambda is taken as 1 by t. N is equal to n naught e to the power minus 1. N is equal to n naught by e. What is 1 by e? 1 by e is 0.368. You can just take it as granted, and you can find it out. If you want to know what is the value of 1 by e, you can get it from the clerk's table, and every e to the power x has a value. For the time being, I can tell you what is the value of e to the power 0. It is equal to 1. It is the easiest value that I can remember, because anything to the power 0 is 1. Similarly, e to the power 0 is 1, and there is a value for e to the power 1. And if you want to know what is the value of e to the power 1, I can calculate it, and I can show it to you like this. Because 1 by e I know 0.368, right? What will be the e value then? E to the power 1. E to the power 1 is equal to how much? I can do it like this. It is like this. 1 by 0.368. 1 divided by 0.368. It is 2.717. Like this. So every e to the power x has a value. X can be 0, 1, 2, 3, minus 1, minus 2, everything. So 1 by is 0.368. So n is equal to 0.368 of n naught. Now we were able to get this result by assuming that lambda is the reciprocal of time, isn't it? Now what time it is? If you substitute it as a reciprocal of time, what is that time? The time in which number of atoms in the sample become 0.368 of the maximum value. Suppose if I had 1000 atoms in my hand, any radioactive material, you calculate the time in which it becomes 1000 into 0.368. What is 1000 into 0.368? It is 368. Wait for 368 of the sample to remain. That means what about the remaining? Remaining have been converted into some other material, either by emitting alpha particle or beta particle. They are not original atoms now. I can't call remaining atoms as parent atoms. Now I have only 368 atoms as parent atom. Okay. So from 1000 to become 368, right? From 1000 original atoms to 368 atoms. That means how much is remaining? 32. Then 632 atoms have been decayed. Wait for that time. How much time you have got now? How much time that sample has taken to reduce from 1000 to 368? Reciprocal of that time is decay constant. So you must be very clear about this. So when you define decay constant is the reciprocal of the time. But you have to explain what is that time. Decay constant is the reciprocal of the time. What time? The time in which number of atoms in the sample will reduce from maximum to 0.368 of the maximum value. Or decay constant is the reciprocal of the time in which number of atoms in the sample will reduce to 36.8% of the original value. 36.8% means if you have 100, it should become 36.8. If you had taken 1000, it should become 368. If you had taken 10,000, it should have become 3680. So what is that time to decay? And its reciprocal is called decay constant. So decay constant will have the units seconds to the power minus 1, hours to the power minus 1, years to the power minus 1, anything. SI system, seconds to the power minus 1. So define decay constant. Decay constant is the reciprocal of the time in which number of atoms in the sample will reduce from maximum to 36.8% of the maximum value. Or the time reciprocal of the time in which number of atoms in the sample will reduce from maximum to 0.368 of the maximum value. So if you start from 100 number to reduce up to 36.8%, how much time is required? Its reciprocal is called decay constant. Okay. Now we will have one more life. We have half-life, right? What do you mean by half-life? Half-life of a sample is the time in which number of atoms in the sample will reduce to half of the n should come to half of the original value. When time grows from 0 to t seconds, the number of atoms in the sample should reduce to n naught by 2. Now we will have one more life, that is mean life. Now why can't I take this as mean life? That is mean life. We have defined a time, right? Time in which the number of atoms will decrease to 36.8%. That is taken as mean life. What do you mean by mean life? Actually speaking, see, first element or first atom, suppose if I had taken Avogadro number of atoms. So how many atoms of uranium now? Avogadro number of atoms of uranium. What do you mean by Avogadro number of atoms? 6.02 into 10 to the power 23 atoms. Out of that, first atom has emitted alpha particle and it has become thorium. Radioactivity started. Second one, third one, fourth one. So like this way it keeps on growing. Now my question is, when will the radioactivity stop? It will never stop. because you see the half-life. Imagine that example. Every time I donate 50% of the money what I have. That is my principle. 50% of the money what I have. That means my pocket will never be unfilled with money. It will be always filled with money. Why? Because if I lose 50% of the money what I have today, I have 50% tomorrow also. So if I have 100 rupees, definitely I will have 50 rupees tomorrow. Day after tomorrow 25 rupees, 12.5 rupees, 6.25 rupees, 3.125 rupees. So I have some money. It will never become zero, because if I have to face a situation where I don't have money in my pocket, I have to donate everything what I should have, right? I am donating only 50% what should I have, what I have. Only 50% of the money I am donating. So I need not worry that my pocket is empty. Every time it is filled. So in the same way, here my argument is, that is, what is mean life? Mean life means, so if 1000 atoms become 500, 500 becomes 250, 250 becomes 120, it will never become zero. That means radioactivity starts at a time, it is a spontaneous process, but it will never end. But the strength of the sample will go on decreasing. That means, sir, that bomb dropped at Hiroshima and Nagasaki, the barium, krypton and all that uranium undergoing fission and the byproducts obtained there, they are radioactive, right? Are they still emitting alpha, beta, gamma? Gamma radiations, especially we are worried about gamma radiation. Are they emitting gamma radiation still now? Yeah, but the strength of the gamma radiations might have decreased. Because the amount of samples, many atoms of uranium might have been converted into some stable atoms. Still some atoms will be emitting alpha, beta particles and gamma radiation. But the radioactivity might have decreased. It hasn't become zero. It might have decreased. Sir, still you are having money in your pocket? Yes. But it is negligibly small. When you come to 1 rupee, 50 paisa, 25 paisa, 12.5 paisa, so what are you going to do with that money? It has become so little that I can say I don't have any money at all. So to such a small value it has gone down. So if you go to Hiroshima and Nagasaki, of course it may be safe now. Even if a nuclear reactor is under problem, people will wait to enter into the nuclear reactor till the activity of the radioactive materials go down. Otherwise they don't enter. They will take some other measures to stop it. So if there is any accident in the nuclear reactor, so the activity will decrease, but it doesn't become zero. So what is mean life? Mean life of a radioactive sample is the time. It is the reciprocal of decay constant, this time itself. Mean life of a sample, it is represented as tau. This is tau, this is capital T. Mean life is the reciprocal of the decay constant. Now, can you define what is mean life then? Because decay constant is the reciprocal of time. What is this one? It is the reciprocal of decay constant. That means that time itself I am defining, isn't it? So what is mean life? Is the time in which number of atoms in the sample reduces to 36.8% of the maximum value. Very simple. So the mean life is the time in which number of atoms in the sample decreases from maximum to 36.8% of the maximum value. Sir, why should you have so many lives, so many time for the sample? Sir, if you want to test whether if you want to explain whether a sample is decaying very fast or very slow, won't you define it by only half-life? Yeah, that is a good number, a good name. Half-life is a good characteristic. If you know half-life of a sample, definitely you can tell me whether it is decaying faster or slower. But we have another one, mean life also. What is mean life? The number should reduce from 100% to 36.8%. What is half-life? The number should reduce from 100% to 50%. Am I right? Now, I will ask you a simple question. Which is greater? Mean life is greater or half-life is greater? Think of which is greater. Is it mean life greater than half-life or half-life greater than mean life? I will write an equation. Tell me whether this is correct. This is mean life. Mean life is greater than half-life. Is it correct or should I change this? This is correct. Why? Because this is Decay, remember, you may be having, you see, half-life is the time in which n should become 50% of n naught, correct? N naught by 2, 50%. Mean life is the time in which n should become n naught to 36.8% of n naught. 0.368 of n naught. So mean life is the time in which number of atoms should reduce to 36.8% of n naught. These are all decays, they are not growth. When you start from 0, you get 36.8% very quickly. But when you will get 50% later. But when you decay, when you start from 100, when it is decreased, you get first 50%, then 36.8. So this is a longer life, right? This is longer life and this is a short life. So what is this? Mean life is greater than half-life, because if you start the decay of a sample, start from 100%. 100, 80, 70 like this, you will get first 50%. That means half-life is over. Then it should decrease to 36.8%. That is mean life. That takes longer time. So mean life is greater than half-life. And remember, half-life, mean life, everything, every term is related. Now, if you want to relate them. So remember, if you want to define decay constant, how do you define the decay constant? It is the reciprocal of the time in which the number of atoms in the sample will reduce from maximum to 36.8%. What is mean life? It is the time in which number of atoms in the sample reduce to 36.8%. What is half-life? It is the time in which number of atoms in the sample reduce to 50%. Now how the decay constant and half-life related? Half-life is 0.693 by lambda. But what is 1 by lambda? 1 by lambda is tau. So why can't I take it as 0.693 into tau? Correct? Because 1 by lambda is tau. This is how do you write it. Okay? 1 by lambda is equal to tau, and okay, t is equal to 0.693 tau, 1 by lambda is equal to tau, t is equal to 0.693 by lambda. This is the story behind all these things. Okay, we'll finish it now. So we have small definitions: half-life, mean life, and reciprocal of mean life, that is decay constant. And decay constant is not the time, it is the reciprocal of the time. Okay, now the relation between half-life and decay constant, and half-life and mean life. You see, now can you tell me that half-life is greater, smaller, and mean life is greater? Because when you multiply mean life by 0.693, you get an answer which is less than mean life, right? Suppose the mean life is 100 years. Say this is 100 years. Then 100 into 0.693, what you will get? 69.3. So this is lesser, but 100 years is greater, correct? So mean life is greater, half-life is lesser. Okay, that is one thing. Secondly, if you want to note it in a graph, so I was explaining, what do you mean by exponential graph? N is equal to n naught e to the power minus lambda t. See, this is the equation. So what does this equation give you? It gives number of atoms in the sample after a time of t seconds. Now draw a graph of number of atoms in the sample here versus time. How will be the graph? It's very interesting now. Till this we were saying that it is exponential decay. What do you mean by exponential? How will be the graph? Is it a straight line? Will it look like a parabola, whatever it is, or a straight line or a circle? It is like this, exponential. See, when the time is 0, what is the number of atoms remaining? What is the number of atoms that you have in your hands when the time is 0? Put time is equal to 0. E to the power 0, you know that value, right? It is 1, correct? Anything to the power 0 is 1. So 1, very good, n equal to n naught. So start from here. When the time is 0, the number of atoms in the sample is n naught, correct? Let the time pass. We will take the help of half-life. What do you mean by half-life? Half-life is the time in which number of atoms in the sample reduce to 50% of the original value. So let this be 1 half-life. Okay? Let this be 2 half-lives, 3 half-lives, 4 half-lives. The graph will be like this, and it won't touch the x-axis at all. Why doesn't it touch the x-axis? Very simple argument. If n has to become 0, what is the time required? Just now we were talking about it. Number of atoms in the sample will become 0 when the time is infinity. Am I right? It doesn't become 0 at all. Why? Because even 50% of the remaining atom will be remaining. We will not be losing all the atoms in a particular time. Definitely 50% of the atom will be remaining. So radioactivity ends at infinite time, and it continues for an infinite time, but it may after certain stage it may not be very strong, but still there will be some radioactive process. N is equal to 0 at what time? If N has to be 0, you see, can I write N is equal to N naught? Okay, I will write it, otherwise I will rub it. Can I write N is equal to N naught by e to the power lambda t? Correct? E to the power minus x is 1 by e to the power plus x. Now when t is infinity, what happens? E to the power infinity is infinity. Anything to the power infinity is infinity, correct? If e to the power infinity is infinity, what is n? N naught by infinity, that is equal to 0. That means this curve should keep on becoming parallel to the time axis. It shouldn't become 0 anywhere. So radioactivity becomes 0, or activity of a sample becomes 0 only after infinite time. So it continues up to infinite time. So now you see, you just see the half of this sample somewhere here, right? You get the first half time. First half-life is the time in which number of atoms in the sample reduced to half of the maximum value, n naught by 2. Can you follow this? Now you have n naught by 2 in your hands. Say 1000 atoms, that is from where you have started, 1000. Now you have 500. Next activity, 500 should become 250. Say half-life is 1 hour. Imagine that half-life is 1 hour. If half-life is 1 hour, then in 1 hour, 1000 atoms become 500. In the next 1 hour, 500 should become 250. That is 1 by 4th of 1000. N naught by 2 should become N naught by 4. Somewhere here. N naught by 2 becomes N naught by 4. Okay. Then, of course, you can continue like this. Half of this, N naught by 8. Say somewhere here. In the third half-life. This is called exponential decay. It is like this curve. So in the first one half-life, it has become 50% lost, 50% remaining. Lost means it has been converted into some other element by the emission of alpha or beta particle. Then in the next half-life, again half of what is remaining, N naught by 4, and like this. And you have one more equation which governs this half-life. It is like this. See, I can explain it like this. And it is like this. Suppose N naught is when the time is 0, N naught is the number of atoms in the sample. After one half-life, we have N naught by 2, correct? Half. Now this can be written as N naught by 2 to the power 0, N naught by 2 to the power 1. After two half-lives, say 2 hours, what is the number of atoms in the sample? Half of this now, N naught by 4. That is N naught by 2 to the power 2. After 3 half-lives, 1 hour, 2 hours, 3 hours totally. It is half of this once again, N naught by 8, half of this. That is N naught by 2 to the power 3. So after N half-lives, sorry, I will use small n. N half-lives, Nt, say 6 half-lives, 6 hours. 10 half-lives, 10 hours. This should become N naught by 2 to the power n. That should be the number of atoms remaining in the sample. N should be N naught by 2 to the power n. This is, and I have used this formula. This is not used in any of the theory problems, but I have used this in entrance exam problem, and I will give you the video. I will connect it again. It's a very easy thing to follow. Okay, N naught by 2 to the power n. Right. So where we are now? So that is the way in which we measure the speed with which the decay will occur. So that is the beauty of the decay process, that is exponential decay. So exponential decay is always like that. It is very fast. Okay. Now one more thing. How do you measure the activity, sir? dN by dt minus dN by dt is called radioactive activity. Some people represent it as A. What do you mean by activity of a sample? Activity of a sample is the number of atoms disintegrating per second. How many total atoms have been decayed per second, and how many total number of atoms have been changed from original atom to another daughter nuclei. That per second is called radioactivity. Activity is measured in disintegrations per second. That is one. That is given the name of Becquerel, who discovered radioactivity. Henry Becquerel. Becquerel, one Becquerel. One Becquerel is one disintegration per second. If one atom disintegrates per second at a moment, then it is one Becquerel. I don't have C, I think, right? One Becquerel is one atom disintegrating per second. That is the SI system unit. SI system. Okay. Then you have some other famous units for measuring disintegrations per second. One is Curie. What is Curie? Ci. 1 Curie is equal to 3.7 into 10 to the power 10 disintegrations per second, or that is equal to 3.7 into 10 to the power 10 Becquerel. 3.7 into 10 to the power 10 Becquerel is called 1 Curie. Sir, why this odd number? It is a activity of 1 gram of radium is 3.7 into 10 to the power 10 disintegrations per second. Do you know what is 3.7 into 10 to the power 10 disintegrations per second? 3.7 into 10 to the power 10 atoms of radium get converted into some other elements in 1 second if you take 1 gram of uranium, because you know the activity is directly proportional to the number of atoms in the sample. dN by dt is directly proportional to n. In 1 gram, how many atoms are there? Those number of atoms show this much of activity. That is and radium is discovered by Curie, Marie Curie. So in the name of Marie Curie, the activity of 1 gram of radium is taken as 1 Curie. See how do we respect the scientists by remembering these values, right? The activity of 1 gram of radium, which is discovered by Marie Curie, is taken as 1 Curie. So what is 1 Curie? If you take 1 gram of radium now, at this moment when you have 1 gram, 3.7 into 10 to the power 10 atoms will disintegrate in 1 second. You see the speed. In 1 second, 3.7 into 10 to the power 10 atoms of radium get converted into some other element and they lose the parental characteristics. So that is the activity of 1 gram of radium. And if you get 2 gram of radium, of course it will double, because activity is directly proportional to number of atoms. So activity of 1 gram of radium is taken as 1 Curie. So 1 Curie is 3.7 into 10 to the power 10 disintegrations per second, or 3.7 into 10 to the power 10 Becquerel, because 1 disintegration per second is Becquerel. So this is how we do it. So that is very important part, and hope you have followed this. And we will, and that makes almost the theory. We will come to the problem part later. Thanks for watching my class. Hope you are following this. All these things are easy compared to the other part, that is electric field and all. So thanks for watching my class. We will come to the with problems in the next class. Take care of your health and be in the theory, and don't leave the theory part and studies. Please do read. Thank you.